Welcome to Green Chemistry. Today we will evaluate the E factor and the process mass intensity, especially for supercritical systems like supercritical carbon dioxide. We will define the metrics, build intuition with a process diagram, run a numerical example, and compare results graphically and statistically for clarity. First, the definitions. The E factor is defined as mass of waste divided by mass of product. E equals m waste over m product. The process mass intensity, or PMI, counts all input mass per mass of product. PMI equals M in over M product. These are directly related. PMI equals 1 plus E, lower is better for both metrics. In supercritical systems, such as supercritical carbon dioxide, we often circulate a large solvent mass, but recycle most of it each pass. That means the effective waste can be small, even though the total solvent flow is large. Let's sketch a simple process with recycle. We have a reactor, a separator, a product outlet, and a recycle loop of supercritical CO2. We will label inlet masses, product mass, and solvent recycle recovery. In metrics, we should count unrecovered solvent as waste, not the recycled portion. Recovery equals 95% is a common benchmark to illustrate calculations. Now, a clean numerical example. We will compare a conventional batch with organic solvent to a supercritical CO2 process. Assume product mass is 100 kilograms in both cases. Conventional case, reagents 120 kilograms, solvent 400 kilograms, auxiliaries 30 kilograms. Total input equals 550. Waste equals input minus product equals 450. So E equals 4.5 and PMI equals 5.5. For supercritical, the circulating solvent is 1,000 kilograms per batch pass with 95% recovery, so only 50 kilograms of SCCO2 count as waste. Reagents 120, auxiliaries 10. Waste equals 80, E equals 0.8, effective PMI equals 1.8. It is also good practice to report the naive PMI that would count all solvent flow, which would be 11.3 here, together with the recycle rate. Formally, an effective PMI that accounts for recycle can be defined as PMI effective equals reagents plus auxiliaries plus unrecovered solvent, all over product. If a separate report is desired, also state the recycle recovery fraction explicitly, here 95%. Let us compare the metrics graphically. First, E factor, conventional versus supercritical effective. Now, the PMI comparison, conventional, supercritical effective, and the naive PMI for reference. To include basic statistics, imagine 5 runs for each process, and we compute the E factor each time. Conventional runs, 4.6, 4.4, 4.7, 4.5, 4.4. Supercritical runs, 0.85, 0.78, 0.82, 0.80, 0.75. We show a dot plot and compute mean and standard deviation for each. Chemically, supercritical CO2 is non-flammable, tunable in density and solvating power, easy to separate by depressurization, and often recyclable at high recovery. Mathematically, the metrics reward high yield, low auxiliary mass, and high solvent recovery. Graphically and statistically, we saw large reductions in both central tendency and spread for the E factor. Always report assumptions. Recovery percent, system boundaries, and whether water or benign diluents are included. To summarize the key formulas, E equals waste over product, PMI equals input over product, PMI equals 1 plus E, and with recycle, effective PMI counts only unrecovered solvent. These metrics guide greener process decisions, particularly in supercritical systems. Thank you for watching. With clear definitions, careful accounting, and transparent reporting, E factor and PMI help us design cleaner, safer, and more efficient processes in green chemistry.